Is that, can you hear me? Cool. Yeah, nice deep booming voice of mine.
Next time you should make it like start at like 7 p.m. and just go until 3.
Much better for
Fair enough.
Not especially.
Yeah, I remember when I was a student, I would go to sleep at like 7. But now that I have kids, that has, I have the 7 a.m., yes.
Okay.
Now it's the complement. Like,
You know the story about Sidney Coleman being asked to teach a class at 9 a.m.? Sidney Coleman was asked to teach a class at 9 a.m. and he replied, "Oh, I don't think I can stay up that late." I realized it was 15 seconds early. Can't do that. You ready, Mr. Clifford?
yeah, sure, let's go.
All right, well, let's go. Here we are, the second half of the third week of TASI. And yeah, I commend all of you who are here at 9 a.m. So let's go to lecture number 3, Mr. Clifford.
Great, thank you. So let's again pick up where we left off. Apologies for my strange sounding voice, feeling a little sore. But what did we do last time? So last time we were talking about the ideas of the scattering bootstrap, where we take very simple basic principles like Lorentz invariance and factorization and just see where it takes us. When applied to amplitudes with one particle soft, okay, low energy, low momentum, we learned that there are certain theorems which dictate that limit for an n+1 particle amplitude, which relates it to a lower particle amplitude, okay? And here I've just written the scaling, which is, in the case of gauge theory and gravity, k to the -1, which just means it's singular, okay? And we kind of finished by deriving charge conservation and the equivalence principle, okay? I wanted to maybe harp on this a little bit. There's something kind of cute about this because usually you would have to put in the infrastructure of thought experiments and like putting people into elevators and throwing them into the sun, all this like terrible stuff. Here we can just say Lorentz invariance and factorization. What this means also is you should think about experiments that test the equivalence principle in kind of a different light. I mean, oftentimes when someone says, oh, well, I have a new theory or this and that violates the equivalence principle, you know that if a theory is consistent, it must violate some of our assumptions. Okay? Now, if their theory only has, say, a graviton, and they say the equivalent principle is violated, then you know that they must be breaking Lorentz invariance or factorization. Okay? If, however, they have those, then very likely they just have another degree of freedom, like a scalar mode or something, which is often in the most sensible theories that violate the equivalence principle, there's just other degrees of freedom in play. Okay, so this is the simplest case of a soft theorem. These are called the Weinberg graviton and a photon soft theorems. There's sub-leading versions, sub-leading versions in some case, which I won't talk about. Now, I did want to talk, however, about another kind of behavior, okay, which is you might think is natural, which is a positive power of k. Okay, amplitudes. Okay, take an amplitude, send k to 0. And imagine that the amplitudes vanish in that limit, okay? The probability of scattering is a 0 in that case, okay? Now, you could probably understand pretty quickly that there's a lot of simple examples of this. The best and simplest to state is the case of a U1 Nambu-Goldstone boson, okay? So right on the action. All this is a scalar field with a shift symmetry. Let me get the normalizations right, because I'll use them. 6 over 6, okay. Okay, just an infinite series of couplings, lambda 4, lambda 6, that are unfixed at present. But this thing enjoys usual shift symmetry. It's a Goldstone boson. It's a low energy limit of like a U1 symmetry breaking, okay? Well, familiar story. Now it should be, I won't go through this, but it should be very plainly obvious that if you compute amplitudes in this theory, there's always a derivative on every external leg, okay? So since there's always at least one derivative on each field, clearly this goes as k to the 1, okay? So maybe the reverse way of stating this, if I didn't want to start with the action and then derive this, you could have instead bootstrapped this in the reverse direction. You could have said, let me write down a scalar field theory. Let me impose this as a condition, okay, using exactly those bootstrap principles I talked about before, where you write a contact term, a factorization term. But there's just a condition you impose. Then in the amplitudes you make, when you send k goes to 0, it vanishes, and you would get these coefficients. In other words, you build an ansatz with free coefficients at each order that are unfixed, that are consistent with that power in k. Okay, so you can go both ways in this business. Now this is very unsurprising. Let me tell you something which is maybe next to surprising, which is, let's say I wanted to up the ante by 1. Okay, so let's say instead I said, well, let's say I want this to go as an plus 1. I take one leg soft. Let's say I wanted it to not just vanish, but vanish doubly. Okay, so if I think of it as a series expansion in k, I want the k to the 1 piece to have 0 coefficient. So the leading soft behavior is k squared. Okay, that is a constraint. Okay, so another way of saying the k to the 1 piece has nominally a coefficient that could have been anything, but I'm going to fix it to 0 in my bootstrap. Okay, now when you do this, something interesting happens. Okay, obviously you can start with this theory because it already gives you a scaffolding upon which you have k to the 1 plus k to the 2 and so on. And then you just demand that coefficient vanish. And you do this with the bootstrap, okay? And I'm not going to do it explicit here. It's a kind of a cute exercise. You can do it 6 particle scattering really easily because there's just like one diagram. But if you do this, what you get is the following. Okay, so what you'll find is that, for instance, the 6 particle vertex will be fixed in terms of lower point. Okay, why is that? Well, it's because the 6 particle amplitude will depend on lambda 6 and lambda 4 squared, right, because of the topologies. You'll get some relation between them given this condition. Okay. Now what you find is that lambda 6 is fixed in terms of lambda 4. Lambda 8 is fixed in terms of lambda 4. Everything is fixed in terms of one coupling. Let me just tell you what that final answer is. So it turns out the first coupling is not fixed. It's unfixed by this constraint. But the others, okay, let me just write them out to be explicit. This is lambda 6 becomes lambda 4 squared over 4, d phi to the 6th. We have some funny numbers, 5/16, lambda 4 cubed, d phi to the 8, and so on. Okay, you can just build these up. The whole point is all the higher order coefficients become dependent only on the leading single coefficient. So we've taken an infinite parameter, an infinite set of free parameters, and we've reduced it down to 1 by making a physics assumption, a physical assumption on the amplitude, which is what we'd call an enhanced soft limit, like better than you would have thought soft limit, okay? Now, if you look at these numbers, you put them into the Encyclopedia of Online Integer Sequences, as we're known to do, you'll find that this is actually a resummation of a known function. Let me write it here, which is even something you'll maybe even recognize, hopefully, many of you. Plus a constant. Okay, so we've actually rediscovered a well-known theory that's in HEP-TH, which is Dirac-Born-Infeld theory. Okay, the scalar mode of DBI. So this shows up all over the place in string theory and cosmology, particle physics, and so on. But one way of thinking about it is if you have a theory with one flat extra dimension, and you have a scalar field phi, which parameterizes the location of the brain, this is the theory of the dynamics of that coordinate. Okay, so phi is the 5th coordinate. Okay, the reason why there's a square root is the boost factor. Okay, we're in 5D flat space, but we have one extra dimension. So phi is, if you like, a Goldstone boson for translation breaking of that brain, but it's also a Goldstone boson for the other Lorentz boosts in 5 dimensions that are broken. Okay, so it's doing multiple jobs because it's a Goldstone boson for a space-time symmetry. Okay, but the point here is that this is not. This is yet a different way of getting at this action without the backstory. Okay? I was saying before, what defines a theory? Well, you could put all those words I just said about extra dimensions and so on, but it's also equivalent to just a nicer property of the soft theorem. Okay? So this gives you kind of a set of instructions for how to build nice theories. Start with many broad assumptions, slowly add them, but don't add so much that your theory disappears. In particular, let's say I just keep going. Okay, let's say, all right, let's just keep forcing this higher and higher. So I say take this and this k to the 3. Okay, this action no longer can accommodate this soft limit. You only have one free parameter, okay, lambda 4. If you just check, it doesn't satisfy this. There's nothing to fix, okay? So it's kind of a general lesson. If your theory has one parameter and you try adding more constraints to it, you'll get nothing, okay? You've like over-constrained it, okay? To over-constrain means to remove the last free parameter you had by imposing that constraint, okay? So as it turns out, this simple U1 Goldstone boson simply can't support that soft theorem. That's just the way it is. So if you like, we've excluded a class of theories. Theories with one derivative per field can never satisfy this property. Yes?
Constraints that you can put on that will get rid of just the one derivative so that it fixes that lambda 4, or?
Good. So indeed, I'm actually going to talk about that in a second. Like, how is lambda 4 fixed? In general, you'd have to find some principle that like fixes like the canonical. It's kind of funny. It's like the one coupling constant. It's like the one thing fixing the dimension and relating the propagator to the leading interaction. So usually that's not fixed. But shortly I will talk about constraints on it nonetheless. Indeed. Yeah, I'll get there in a second. Good. So as it turns out, this example of like a super duper enhanced soft limit doesn't apply to this. But if you add more derivatives to your original action you're interested in, you can accommodate it. Okay, so I'm just going to write this mainly to introduce a theory that will be useful when I talk about double copy. I'm kind of like rearing to kind of start talking about that for real. But it's a nice way to introduce it, which is that if I demand this soft limit, it's actually enjoyed by a theory I'm only going to write down its action schematically, called the Galilean. Okay, so this is something that showed up first in phenomenology and then in kind of modified gravity. The Galilean you can think of as the longitudinal mode of a massive graviton. So in some sense, it's like the cousin of the pion being the longitudinal mode of a massive gauge boson. But it's just, if you like forget that backstory, it's just a scalar field with a big shift symmetry, like a really intense shift symmetry. Okay, so what is that shift symmetry? So it has terms that look like d phi squared times dd phi times dd phi squared, dd phi cubed, okay, and then so on. Depending on how many number of dimensions, this would truncate and so on. Okay, and the point here is that this k cubed fixes this kind of structure. Okay. And I should probably even say, like, the reason why it's called the Galilean is not because it's non-Lorentz invariant. It is Lorentz invariant. The reason it's called the Galilean is because it has a shift symmetry where phi shifts by constant, but also by b mu x mu. Okay, like a Galilean, like quote unquote relativistic version of a Galilean shift that you know if you're doing let's say fluid mechanics or like the Navier-Stokes equation, but everything's Lorentz invariant, okay? Don't worry about it. Everything's Lorentz invariant. And there could be even other, even more enhanced symmetries, okay? But the upshot is like, this is when I say Galilean, I will mention it a number of times. People think about it with cosmology and as an exotic theory. It's very strange. This is what I mean, okay? Good, okay, so good, so that's actually all I want to say about soft things. I want to return to this question of lambda 4, and this is going to be my way of kind of not quite switching topics, but like maybe let me kind of zoom out a bit, okay? Right now we've decided that we could kind of impose symmetries, or sorry, impose principles like properties of amplitudes and kind of get theories out. But there is still a question of like the free parameters left. Okay, are those just anything goes, lambda 4? Or let's say if I was even looking at the Nambu-Goldstone boson theory, with free couplings, if I didn't demand any specialness whatsoever, is lambda 4, lambda 6 arbitrary? Okay, is there a theory somewhere in theory space that gives me whatever value for those I want? Okay. Now, if you were like a very naive effective field theorist, you would say yes. You'd be like, okay, I have an EFT. Those couplings can be anything, okay? Because like, you know, they're free, okay? But as it turns out, from many different directions, but certainly from the point of view of amplitudes also, there's actually constraints on these couplings, okay? And these are broadly called positivity bounds. Okay, if you've heard these words, they essentially mean that the couplings cannot be any number you want. They're like bounded maybe from below or above in some interesting way, okay? From the point of view of just writing it down, it's very confusing why that would why there would be any constraint, but I want to talk about that now, okay? So we're still in the kind of second unit of what I was wanting to talk about, which is infrared UV. This is when we start connecting infrared to UV, okay? So this is the first place where we're going to see kind of an interesting interplay between like low energy stuff and high energy stuff, okay? So this is called positivity bounds. It's kind of it's been a cottage industry for a while. I mean, kind of in the background. But in recent years, there's been a lot of like new technology and like variations of this that have become quite powerful. I'm not going to be able to cover those and do them justice, those very new developments. But I thought for culture, everyone should actually know like what are people doing when they say positivity. Okay. So the simplest example, which I think is at least instructive to see why low energy EFTs have any kind of constraint is just, let's take this U1 Goldstone theory. Okay, in fact, let me just look at its first coupling. Now, nominally you'd say, oh, lambda can be anything, okay, whatever number you like. But let's probe that, okay? So here I'm going to be repeating a very elegant, kind of interesting argument from Alan Adams, and Nimar Khani Hamed, and others in this seminal paper from, I think, 2003, or 2000 something. But here's the argument, okay? This seems perfectly consistent, but let's consider this about a background, okay? So let's take phi, and let's set it to some vev plus a fluctuation field, okay? But we're going to do something a little snaky. This vev is not going to be a constant, okay? This vev is going to be like an ether-like background, okay? C x mu, okay? So C mu is just some constant vector. It could be actually time-like or space-like. It doesn't matter. Of course, this is a classical background, so it should satisfy the equations of motion, and it does. Okay, I'll leave that to you to see as an exercise. Basically, the Euler-Lagrange equations of motion are like d mu over another current. The another current just is c mu, okay, or a function of c mu, so it's a constant. So this is a bona fide classical solution. You could think of this almost as like the analog of a fixed electric field, a constant electric field in space. Okay. So, okay, let's not worry about the fact that it goes off to infinity minus infinity for the moment. You probably should, but let's not worry about that yet. Let's just study fluctuations of little phi about this background. Okay, so I'm not gonna, let me not bore you with that expanding details, but you just plug this into that. You get an effective action for little phi, and then you can look at its dispersion relation. Okay, so what they showed, okay, let me just jump right to the answer, is if you go to background field method and write down the dispersion relation for this particle, you get the following. And I'm working in small lambda, and I'm working in a limit where C is not outside the regime of the EFT. Okay? So as usual, I don't want to be picking C so that's like higher than my ultraviolet cutoff. I need like a weak field perturbation. Okay? That's required. So we're still doing consistent effective field theory. But what you get is the following for the dispersion relation, the linear dispersion relation for the fluctuation field. Okay, of course, there's nonlinearities and so on. There's a whole tower here, but like if you just look at the quadratic term, this is the analog of like D'Alembert and phi equals 0, like the Klein-Gordon equation. Okay, so of course this term is the usual Klein-Gordon equation, but there's a correction. Sorry, that depends on lambda. Sorry, that's important. Okay, and also the background. Okay, so the background together with the coupling induces a correction. Okay. Now I'll leave this to you, but you can just study the causal structure of this and ask a basic question, which is, did your light cone fatten or thin? Did things start going superluminally or subluminally? As it turns out, that just depends on the sign of lambda. Okay? In fact, it doesn't even matter if C is space-like or time-like. Okay? But your light cone will either allow for superluminal propagation or subluminal propagation depending on the sign of lambda. So in particular, if lambda's positive, it's subluminal. And by that, I just mean in the original theory, if C was 1, you're going faster than the speed, slower than the speed of light in this background, while in this case, it would be superluminal. Okay, so they then make kind of the little fast and loose here. You should hopefully be a little skeptical because I'm talking about a speed of sound. I'm not making important distinctions between phase velocity, front velocity, and so on. But nominally, they would say, oh, superluminal bad, this is positive. Now, in all UV completions that have ever been written down, that is true, lambda greater than 0. Okay, and you can apply similar arguments actually to even like a gauge theory. So another classic example is the Euler-Heisenberg action. Okay, not Einstein-Hilbert, but Euler-Heisenberg, which is just the theory of the photon below the electron mass threshold. Okay, so this is some minus 1/4 f squared plus lambda ff squared plus something called lambda tilde f tilde squared. okay? Just writing down higher dimension operators. These coefficients, lambda, lambda tilde, are calculable. They just depend on the fine structure constant and the electron mass. The same type of logic tells us that lambda, lambda tilde is greater than 0 if you want subluminal propagation, okay? In terms of the photons in that case. Okay, so this is, okay, what did we learn here, okay? When people say positivity, there's always something like this. It's like something bad is happening when something becomes negative. But I wanted to, at the start here, just tell you a caveat emptor with this story, okay? Superluminality is actually not a great diagnostic to throw out theories. And the best way of saying why that is because of an example. So in the standard model of physics, there are superluminal photons precisely in this sense. Okay, this is like a piece of lore that people don't actually know, but there was this wonderful paper from like 50 years ago, 40 years ago, by Drummond and Hathrell, who looked at the Euler-Heisenberg-Lagrangian in the standard model, so integrating out the electron, in the presence of gravity and the photon. Okay, so the idea is, in that theory, you also have f squared r. Okay, curvature, gravitational curvature corrections too. You can compute those coefficients. Those are like finite loops. Okay, so these are known coefficients in the standard model. Okay, there's some coefficient here. If you take that theory with those coefficients and you take a photon outside of a black hole, I think moving in the parallel to the horizon but polarized radially, it travels faster than the speed of light. Okay. Now, of course, the standard model is okay. Don't worry. It should be fine. The point here is that there's an issue with this general argument that superluminality bad because in the presence of gravity, certainly, there's a long-range force. So we could talk about it as speed, but in the end, it has to crawl out of that potential, that gravitational potential. There's a redshift. There's like gravitational dynamics, which is why, of course, the right thing to compute is not some local speed, but a Shapiro time delay. Okay, this is the classic, correct asymptotic way to determine consistency, which is see if you can really send a signal from like some deep past to the future and get it there before you. Okay, this is maybe like a warm-up to doing that correctly, but I just did want to say that this is, especially in the presence of long-range forces, background metric, caveat emptor. Okay. Now, with all those, yes.
So who did that work with the gravitational coupling?
Who did? The question was who did this work with computing the Euler-Heisenberg-Lagrangian with gravity and electromagnetism below the electron mass and showing that it is superluminal. It was Drummond and Hathrell. Okay, so even in their original paper, they pointed this out and said, well, this is not a wavefront velocity. The usual statements, okay? They even knew all these things, and it's been litigated since. Everyone agrees in all possible ways that it's okay. Don't worry. But it tells you that you could be a little sloppy and convince yourself of too strong a statement. Now, what is great is that from the point of view of amplitudes, there is an analog of this type of statement, which is rigid, hard, and does not have these kinds of subtleties, or at least the subtleties that exist, you can identify precisely the assumptions. And that's what I want to talk about today, at least in this part of the talk, which is the amplitudes version of this. Okay? And what it's going to do is it's going to use information about the ultraviolet and the infrared to bound these couplings and tell us they're positive. Okay, so why don't I keep going, since I guess folks are here. Okay, so what do I mean by that? So let's talk about dispersion relations. Okay, so this is technology that existed like ages ago. It's used for theory of pions. It kind of became forgotten lore and then remembered, and now it's kind of had a reinvigoration, not in the context of the strong interactions, but in terms of gravity and like kind of other types of theories. But what's the basic idea? So it's very easy to state, okay? Let me give you an amplitude in some theory, okay? In some sense, I want to be maximally agnostic. You could think of it as this scalar theory, but the whole point is you don't know the Lagrangian. You don't know the UV, you don't know anything about it. I'm just giving you A. Okay, and let's take the forward limit, where t goes to 0. Okay, now of course, even in saying this, the forward limit has to exist. So if you have t-channel singularities, as you would have from a long-range force, like a photon or a graviton, this isn't defined, okay? Which is why that's an important thing to not have if you want to do what I'm about to do. Of course, if you have one, there's ways around it, but I won't talk about it. But the idea here is that let's take the forward limit. It's the simplest case. What you get, if you think about it as a series expansion in S, is the following. Okay, it's just a power series in S. I'm implicitly thinking of this as like an effective field theorist, expanding your amplitude at low center of mass energy in the forward limit. Okay, now hopefully that's clear. Now, you all know here that these CNs, okay, these are like dimensionful couplings, 1 over lambda squared, 1 over lambda to the fourth, and so on. These are Wilson coefficients, or at least they contain all the information about the Wilson coefficients, right? If you write down an EFT, lambda 4, lambda 6, these are Wilson coefficients. Those things get buried inside those CNs, okay? So these are proxies to the actual coefficients in the effective field theory. These are the things we want to constrain, okay? Good, so what do we do? Okay, it's actually very simple in the end. What we do is we write a dispersion relation is basically a complex analysis trick to extract the CN from the amplitude, and then use Cauchy theorem to relate that CN to other things that you know about. Okay, that's basically it. Okay, just like when I mentioned BCFW recursion, as complexify something in Z and like relate it to things at other Z's. That's exactly the same thing here. Okay, we're using analyticity. And we're using it to extract CN. Okay, so how do we get CN? You can just use the residue theorem. So ds over s to the n plus 1 times a s t goes to 0. Okay, where I have some contour here, I guess, let me call this gamma. Okay, so right now this is just tautology. I'm just like extracting the s to the n power with the residue theorem. It's useful to think about this in the complex S plane. Okay, so I feel like this gamma is some contour that just wraps the origin. Okay, because I'm just picking out this pole. Okay, this is just going to bring down the s to the n piece of this and then pick up that residue. Good. All right, so that's all this is at present. But now of course, you can anticipate the trick is to take this contour and blow it up. Okay. Now to do that, we need to know that this thing is analytic. I'm not going to prove here why the S matrix is analytic, but the kind of basic underlying reason is causality. It has to do with the fact that when you have causal Green's functions, the position and time domain Green's functions have to have 0 support in certain regions, which then dictates analyticity in the complex plane for momentum. Okay, I can elaborate on that afterwards if people care, but the idea is that this thing is analytic except for kind of junk on the real axis, which corresponds to like particle production, like massive particles coming to life or branch cuts from pairs of particles coming to life. Okay, so this is the usual statement that if you look at an amplitude as a function of S, the discontinuities correspond to like a state going on shell or something, right? So, there could be, single resonances, there could be multi-particle states. Okay, I'm just drawing this as like squigglies here. Okay? But the point here is I can take this contour and I can deform it in this way. Okay, it's like kind of double Pac-Man picture. Okay, let me get the arrows right. Okay, where I have, if you like, you can think of it as an integral on this wing. Okay, like these two integrals on this real line. There's two integrals on the negative real line. Then there's the boundary. Okay. Now, why do we do this? Well, we do this because something very nice happens. So if I just continue this equation, write it this way, we have an integral of minus infinity to S0 plus integral. Okay, actually, let me define S0 to be, if you like, some value which is like below the gap of the first massive particle that shows up. Okay, so we can think of S0 here as kind of where this thing gets caught on the branch cut or whatever poles are here. Okay, so I'm immediately assuming there's kind of a gap where there's some heavier particle that wasn't in my EFT, but I'm hitting it. I'm finally reaching it and producing it. I'm going to define that as S0. Okay, in which case the integrals over the two wings are this times ds over s to the n plus 1 times the discontinuity of a st goes to 0, where discontinuity just means like the amplitude evaluated s plus I epsilon minus the amplitude evaluated s minus epsilon I epsilon. Okay, it's like literally the discontinuity between evaluating on these two sides. Okay, now plus boundary term. Okay, so in terms of the physics, what's all the physics? So we started with something extracting infrared information, but we use analyticity and center of mass energy to relate it to all the intermediate energies along the real axis, plus a boundary term, which is UV. Okay, so like we use complex analysis to do, if you like, UV IR mixing. IR by Cauchy theorem is like everything between UV and IR. Okay, now here's where we have to start assuming things, but we know precisely what we're assuming. The boundary term. Okay, how do you compute this? You have to know the UV. Okay, now thankfully there is general arguments that this boundary term will vanish. Well, of course, it depends on n. But there's a general unitarity bounds called like the Froissart bound or Regge boundedness, which tell us that A should be at least polynomial bounded, and given whatever assumptions you have, or even bounded by like s to the 1 or s to the 2. Okay, so there's general arguments from unitarity with assumptions about various things that this is 0. Certainly, if n is big enough, if n is like 20, you're safe because A is not going to go as s to the 20. That's definitely not a healthy theory. Okay. So we're just going to assume the boundary term is 0, and if you like, those are just based on the assumptions that go into the Froissart, Martin bound, et cetera. Okay, but it's an assumption. Okay, like there's definitely like there's bodies buried here, but like I'm telling you where they are. They're right here. Okay, that was a little dark. So the discontinuity. Okay, this is the imaginary part of the amplitude. Okay, that's just complex analysis. So let me maybe do this in one step. So this discontinuity, disk A is equal to 2I times the imaginary part of A. Okay, and the imaginary part of A is related to the cross-section by the optical theorem. Okay, imaginary part of A is like S sigma, like the cross-section times some power of S. Okay, times 1 power of S. Okay. So this is S sigma of S, forward cross-section. Okay, that's where the positivity will enter. Okay, good. Now, if you take all these expressions, put them in, here's what you find. Okay, and here I have to actually be a little. There's an important thing I've been a little fast and loose with, which is I have 2 integrals over like one side and the other side. You can think of this as the S channel poles, and these are the U channel poles. Okay. Naively, they could just be different things, but for simplicity, if I imagine there's crossing symmetry, okay, SU crossing, then these are the same quantity. They're the same thing being evaluated. Now, as it turns out, there's signs I have to care about, and if there's crossing symmetry and n is odd, then this just becomes 0. Okay? I'm not going to work through it, but basically it's just the Jacobians of like flipping the ds and minus ds around. And it tells you that this polynomial doesn't have odd powers in S. Okay? That's really just, in some sense, an output of crossing. Now, on the other hand, if n is even, something very interesting happens, which is Cn, like we just plug in all these expressions, we get 1 on 2 pi, integral from S0 to infinity, ds over s to the n, sigma of s, okay, the cross section weighted by ds over s to the n, integrated over some physical region, which is positive if you're in a theory that's not free. Okay, this is positivity, like a rigid positivity. Okay, like because it's proven in some sense very axiomatically. What this says is write down any UV completion you want. Like literally take any amplitude you know in any book you have for whatever stringy compactification or this or extra dimensions, this and that. Take the Fourier limit, send like series expand it, every coefficient will be positive. Okay, if it's not, you've violated some important axiom, either unitarity, analyticity, which is causality, or Lorentz invariance. Okay, yes? Yes, very good. So sorry. So this argument assumed I had a mass gap because things get very tricky for many reasons if I have massless particles. This is directly connected to why there's a subtlety in Drummond-Hath rule from long-range forces. For instance, if I had a gapless exchange particle, there would be no forward limit. If this merged all the way to the origin, I now have branch cuts connecting, massive subtleties. So indeed, kind of litigating through those subtleties carefully is crucial. This argument strictly requires that, for sure, requires a gap. It's true in some theories, and certainly if you could, in some theories, in some theories you can kind of parametrically try to argue that at some order in perturbation theory you could ignore the branch cuts that go to the origin, but in general you just have to deal with it. And it's not trivial to deal with. In fact, one of the main thorns in all of our sides for trying to place rigorous bounds in gravity is the graviton's gapless, and it's just floating around, ruining all these statements. So it's not super straightforward in that sense. Okay. Now, one thing I do want to say is if I kind of commit to this mass cap, you could also do other things, which is kind of cute, which is you can derive, I don't want to say dimensional analysis, but naive dimensional analysis. So there's this idea, often spoken of in kind of particle physics circles, where if you have an EFT, you have a bunch of coefficients in your expansion in some cutoff, they should all be of order the same cutoff, right? You shouldn't have like some operators with one big cutoff, one with another cutoff. I just want to mention this because it's easy to kind of tack onto this expression. Okay, you can do the following trick, which was done by Rattazzi and Bellazzini, like I think a couple years ago, which is it's like deviously simple. I kind of like it, so I'm mentioning it. Okay, so do the same thing we just did before. S t goes to 0, but let me multiply this by a form factor. Okay, let me call this form factor S0 squared over S. Okay, where S0 is where the gap is, because I've assumed there is one. Okay, where F has the property, okay, such that F of X is greater than 0 if X is between 0 and 1. Okay, what's the purpose of this? Okay, so the purpose of this is to write down a function here, which is going to be positive, just like definitionally constructed to be positive, throughout this integration range. Okay, so it's like a little form factor in here. So it's going to be like a weighted cross-section, where the weighting is the weighting of my choice. I want it to be positive because I want to be able to write a greater than 0 at the end of the day. Okay, so if I put a form factor here that had negative values, then I can no longer argue that it's positive. Okay. Here's a very simple example of this. So you could choose, for example, f of x. F of x is equal to 1 minus x to the k. F of x is equal to 1 minus x to the k. Okay, if you plug this in, okay, you'll get something that's positive. That's what it is. So right hand, greater than 0 is on the right-hand side. But you'll notice that the left-hand side has two terms. Has a 1 term and an x to the k term. In other words, a 1 term and an s to the minus k term. So it's actually going to pick out two separate Wilson coefficients. Okay, it's going to pick out a Wilson in fact, this thing here is Cn. But because of that f, for this choice, I get S0 to the 2k times Cn plus 2k. Okay, and this whole thing is greater than 0 by positivity because I chose this to be positive. Okay, so this is a little amusing because, okay, if I change variables from n to something maybe a little nicer, it tells me that Cn over Cm, two Wilson coefficients for different powers of s, they're actually bounded by S0 to the n minus n for this gap. Okay, so in some sense, it's a bound that tells you that if you try like squeezing one of those scales in an operator too far from the mass gap, you're in trouble. Okay. Anyway, okay, so I could keep talking about this. I had more to say, but I kind of want to just I want to push forward. So maybe I'll just summarize the kind of big picture here. Effective field theory gives you the naive intuition that everything's free, but there's actually a whole range of positivity bounds that constrain parameter space. You can think of this as almost like a convex hull, like a shape in space with just certain regions that are excluded. If you've heard about things like the EFT hedron, the effective field theory hedron, that's like a polyotope whose interior is consistent and whose boundaries correspond to like more elaborate and interesting types of positivity bounds, in particular where t is no longer 0, but non-zero. There's also so-called null constraints and moments, and there's kind of a whole, the whole library now of these things, kind of attacking this problem in different ways. What's the ultimate goal? I think, to just sculpt out the space of consistent coefficients. Okay, maybe we could be so lucky that it'll like narrow down to something amazing, something unique. But if anything, we should just know like whether theories are healthy or not. Okay. And in fact, some of this even could have phenomenological implications, because of course there are REFTs that we're testing, like the standard model effective field theory. There are higher dimension coefficients. They are bounded. Okay. Cosmology, there's higher derivative coefficients. They're bounded. So these bounds can have some back reaction on what you might care about in experiments. Okay, good. Any questions about that? What's that? Oh, so this thing is only being evaluated between 0 and 1 because of the way I defined it, because S goes from S0 to infinity. So I only care in this window, yeah. But thanks for that question, yeah. So I kind of taken care of that here. Yeah. Good, okay, so let me now, okay, if there's no other questions on this, let me move to the last kind of chapter of what I want to say in my lectures. And this was great because this allowed me to introduce a lot of the kind of theories that will show up. The last chapter, if you recall, because we've gone through the bootstrap tutorial, we've gone through infrared UV. The last chapter is hidden structure. Okay. So you've I'm sure noticed that in the previous lectures, we've been doing a lot of kind of reinventing the wheel. I can talk all day about how amazing structures are and how beautiful it is, yada, yada, yada. But if it tells you nothing that you didn't know yesterday, to me, I don't care. Yeah, okay. So today, let me tell you things you don't know and the Lagrangian doesn't know, okay? And I'm going to harp on, well, kind of a constellation of structures related to something called the double copy, whose basic upshot is that theory space is diatomic, okay? Theories are diatomic. They come in pairs that clump together to give other theories. The word equation is this, gluon squared, in terms of scattering amplitudes, is the graviton amplitude squared. We saw this already at 3-point. We're going to do this at 4-point and n-point. Okay? But right at the start here, I wanted to emphasize that this is not just a gauge gravity statement. Okay? Here's another equation which is true, pion, as in the scalars of the nonlinear sigma model, chiral Lagrangian. Okay? This also squares to something. Okay? This squares to the Galilean. Okay? We can even take asymmetric products, okay? And again, this is schematic, but we'll see very explicitly with formulas what this means. You can take a gluon, and then you can take a pion. Okay? You can take their asymmetric product, and you get a Bohr-Infeld photon. Okay, what could this possibly even mean? I mean, at the level of scattering amplitudes, you can take gluon amplitudes, pion amplitudes, mash them together, and get Bohr-Infeld photons. Yeah, yes?
These are all for massless particles?
These are all for massless particles. If you want to add masses, you could KK reduce in one private extra dimension and add masses. So masses is something you can add. You need to add if you want to have implications for certain physical problems, like gravitational waves, which we had to grapple with. But yes, you can add masses. Yeah. Yes?
Is this commutative as in you put glue on first?
Yeah. This is an unordered product. Yeah, it's really like multiplication, because actually the operations are addition and multiplication. Yeah, so you'll see why. I'll be less schematic, but this is just a little bit of the product of theories. There's this awesome review on the double copy by Radu Roybon and Zvi Byrne and J.J. Carrasco, many of the discoverers and Henrik Johansson, the discoverers of many of these dualities. Where they have like a multiplication table, like theory, and just like they have like Susie, no Susie, they have like Higgs phase, this, that, Coulomb. It's a whole mess of stuff. It's awesome, okay? But if you have a theory that has a name and one parameter, there's like a decent chance it's either on one or the other side of this mapping. Okay. Good. I wanted to say one more thing, but okay, let me just push forward. So let me just tell you what it is. Okay, let's start very simply. Okay, maybe start with a reminder. Oh, here's the thing I wanted to say. Yeah, this is important. This is not, I'm not making up different rules for each of these. Yeah, this is important. Literally the same rule applies to all three of these. So the workflow for this applied to this gives graviton, applied to this gives Bohr-Infeld. There's no change of rules. It's exactly the same instructions, which I'll show you in a second. Okay. Also, I'll say one more thing. These aren't just kind of coupled together with these squaring relations. They're also linked kind of in other directions, all through gravity, in a way that I'll also discuss. Okay, but let's stop being abstract. Let's actually do something. Okay, so let's talk about what's called a version of double copy, which is called color kinematics duality. Okay. It's also known as BCJ duality, Byrne, Carrasco, Johansson. Really, in my view, like an absolutely seminal work. Okay. I think it's gonna be in textbook someday. That's my opinion, but you can decide yourself if it's that interesting. Let me start still at the basic level. Okay, we're gonna start at A3. I know we discussed this before, but let's really unpack it. Okay, we have Yang-Mills. We have a structure constant FA1, FA2, FA3. Sorry, FA2, FA3. And then we had the kinematics, which I'll just write out one last time. P1 E3 minus P2 E3 plus yada yada. Okay. Now remember, when we went through this exercise, we derived the kinematic piece first, realized it was antisymmetric, got worried, and then added an antisymmetric structure constant to make the whole thing bow-symmetric, right? Okay. Now, notice that I have kind of two objects with the same symmetry. Antisymmetry in any two indices and cyclic. Okay? One is an honest to goodness tensor, the other is a kinematic factor. Okay? So if I just kind of squinted at this and said, hey, this is kind of like a structure constant, right? It's like antisymmetric in indices, which are momenta and polarizations, cyclically invariant. Let me just commit to that, okay? Let me just be like, let me just see where this takes me, okay? And by this I mean, what if we start replacing these willy-nilly? Okay, the basic mantra here, and this is why this is called color kinematics duality, is take a theory with color, okay? Color has to satisfy Jacobi identities, antisymmetry properties. Replace it with something that is kinematic dependent, that satisfies the same identities. That's the entire essence of it, okay? Now the point is that anything in your theory, all your consistency conditions and word identities and this and that, soft theorems, yada, yada, they all depended just on basic facts about FABC, which is antisymmetry and the Jacobi identity. So if you can do this replacement wisely and intelligently, then you'll get a new theory that should also be consistent. That's the basic essence of this. Take a number, a tensor of couplings, replace it with something kinematic dependent, and try to build something sensible. Now, let's do that here. Okay? In fact, first we'll go in the reverse direction, this way. Let me take A3. Okay, let's do the easier case. If I just replace this with a second color structure. Okay? In fact, I could just say this is A1, A2, A3. I could just replace this with AF, A1 bar, A2 bar, A3 bar. This could even be F bar for some other color group. Okay? So this is a theory. Obviously, it's a simpler theory than Yang-Mills. Let me tell you what it is, because it's going to show up a bunch a bit later. BAS, which denotes bi-adjoint scalar theory. Let me just write the Lagrangian, because it'll be easier to convey what's happening. Okay, it's a very simple cubic scalar theory. Okay, so the Lagrangian bi-adjoint scalar theory is just 1/2 d phi a bar d phi a bar plus f abc f a bar b bar c bar phi a bar phi b bar phi c bar. Okay, it's got a cubic interaction. Okay, only cubic. It's just the theory where I've decided to invent here. And it's got two structure constants. Okay, so it's called bi-adjoint because phi is an adjoint under one color and under the other. They could be different groups, but let me just make it the same just to make life simple. Doesn't much matter. The reason it won't matter is because I'm going to take those color structures and throw them away anyway, so it won't matter. Okay, but you can see that in some sense, Yang-Mills is this theory, but where f, a bar, b bar, c bar secretly has momentum. You could think of it that way, okay? But this is why I'm doing this. Good. Now there's, of course, another thing we can do, which is we can do the opposite, which is take the kinematic, the color structure and replace it with a second copy of the kinematic structure. Okay, and of course we already saw what this is. That's GR. Okay, so let me not. Okay, let me just to be explicit. E1, E2, P1, E3 minus P2, E3, yada yada yada, whole thing squared. Okay, so we saw this as a square, but I'm reinterpreting this as taking one of the color structures and replacing it with the kinematic structure. Okay. Good. Any questions about that? So I'm really just restating those products we saw before, but maybe a slightly new light as an active procedure of replacing color with kinematics. Yeah. Oh, yeah, you could. Yeah. So I'm doing it because double copy works in any dimensions, and maybe I want to emphasize that. But if you want, yeah, use spin helicity too. That's fine. Yeah. I should have also emphasized, yeah. these properties will be d-dimensional, which is why I'm going to treat them in d dimensions. Actually, I think in the 4D example I'm going to do, in the 4-point example, I'll go to 4D, because it's just easier. Yeah. Good. All right, so that's all still trivial. You should hopefully understand, because that's just Lorentz invariance. Let's do the first interesting case, which is 4-particle scattering. Again, this one's kind of truly magic. Okay, so let's take 4-point. This was all 3-point. Let's take 4-point. Okay, A4. Okay, for the moment, I could even kind of be agnostic about what theory I'm talking about. So for the moment, I could be talking about, let's say I'm talking about Yang-Mills just to make life easier. Okay. Let's say I wanted to take the 4-point amplitude and apply double copy. So what I first want to do is organize everything into S, T, and U channels. Okay, let me tell you what I mean by that. So this is CS NS over S plus CT NT over T plus CU NU over U. Okay, where CS, I don't have to write this out, but this is like A1, A2, B, F, A3, A4, B, CT, C, the obvious things. Okay, CS, CT, and CU are the different contractions of color structures across each channel. Okay, so color structure is C. These are just numbers. Okay. NS, NT, and NU is the kinematics, the momentum and polarizations if you're in general D, or your spin or helicity brackets. ST and U are the poles. Okay. Now you might say, wait a minute, what happened to my contact term? Okay. For instance, if you're doing like Feynman diagram, you'd say, okay, this is S, this is T, this is U. Okay, what happened to this guy? Quartic contact, if you use Feynman rules. That's okay, it's around. I've just chosen to absorb it into one of these terms. Okay, obviously, if NU had a term linear in U, that's a contact term. If NT had a linear T term. So this allows for contacts, of course. Okay, just means that there's kind of pinching terms. Okay, so no matter, and the kind of key point here is I'm not using Feynman rules. You can use whatever rules you want, whatever way to compute. Just take your amplitude and put it in this form. Okay, that's all you have to do. All right, just do that. Of course, there's freedom in that. You should see, because of course there's identities between the CS plus CT plus CU equals 0. Okay, this plus this equals 0. That's a Jacobi identity. So there's freedom in how you arrange things in this form. It's not unique, but just put it in a form of this type. Okay. Now you can see why we're doing this, because this puts C and N, kinematics and color, on like equal, even-looking footing. But let's unpack that. How equal of a footing are they on? Okay. Let's think again about. Again, we want answers that are robust, independent of how we computed them. I don't want to make statements about Feynman diagrams that are gauge dependent, this and that. So a very natural question to ask is, if I change my gauge fixing, if I change my field basis, how do these N, S, N, T, N, U change? Like let's say someone used a different action to compute the same physical thing. The representation should change, but A4 will be the same, because that's physical. Okay? So what that means is something's got to change, which means NS, NT, NU have to change. The only things that can change under a gauge transformation or a field redefinition. So let's define that as, okay, let's imagine we do a change of coordinates. We go to a new Lagrangian that describes the same physics. NS will go to NS plus delta NS. NT goes to NT plus delta NT, and so on. Okay? So here these delta objects contain this unspecified kinematic information, and even like stuff that's like in your field redefinition. Random parameters you decided to invent, it's all jammed in here. Okay, now if this is how the numerators transform, you'll see that the amplitude, A4, has to transform also, but it better be invariant, because it's invariant under those transformations. So if you compute delta A4 induced by this, it better be 0. And delta A4 is just these delta NS's sitting in front of each of these pieces. So this thing is just CS delta NS over S plus CT delta NT over T plus CU delta NU over U. And this has to equal 0. If it's not equal to 0, you've done something illegal. The theory you're in is not the old one. Okay. Now this is some identity that involves kinematics, like deltas involve kinematics and color structures, but it's some identity that has to hold for any on-shell configuration, and it involves CS, CT, and CU. Now there's only one identity involving CS, CT, and CU, which is the Jacobi identity. Okay, it's a little bit like our argument about equivalence principle. It's like you want some identity amongst momenta, it's momentum conservation. You want an identity amongst color, it's the Jacobi identity. Now what that means is that each of these terms has to be equal. Okay, so that's a direct implication, but you can even check. You could just do this yourself and see. But what you learn is, in fact, okay, there's no room there. There's no eraser. Statement is that delta ns has to be proportional to s, delta nt has to be proportional to t, and delta u has to be proportional to u, all with the same proportionality constant. Okay. Okay, so let me write it out. Let me stop writing each one in turn. So delta s equals alpha s and yada, yada, yada. But it's the same alpha, okay, for each of them. They have to be the same proportionality constant so that they're all weighted the same. Okay, so that's an interesting fact. What you'll also notice because of this, so yeah, let me write the second one. Nt is alpha t and so on. You'll also notice that delta ns plus delta nt plus delta nu is 0 because s plus t plus u equals 0. Okay, what does this mean? This means that the quantity ns plus nt plus nu is invariant under field redefinitions and gauge transformations. It's gauge invariant. Okay, the n's themselves aren't gauge invariant. You change gauges, ns will change. But the sum of ns plus nt plus nu has no variation. Okay, that's interesting. That means there's something stable about this. Now, what we're going to see, okay, let's prove that now, is actually that ns plus nt plus nu is 0 on shell. Okay, we're going to show that next in Yang-Mills. Like literally just compute Yang-Mills amplitudes any way you like, and you will find this triplet sums to 0 on shell. Not off shell, but on shell. Okay. Maybe I can do this quickly. You know what? Let me do it faster than I would normally do it. Okay, if you want to see details, you can look at my old TASI lectures. I'm only going to jump to the end here, which is you can write a. Actually, how much time do I have?
20 minutes.
Oh, 20 minutes. Okay, cool. That's that could be doable. So, good. Yeah, let me still jump. Better to jump. So, but let me kind of tell you the instructions for how to do this calculation. I'm going to leave it as an exercise. It's pretty simple. Okay, let's take Yang-Mills theory. We already wrote down this amplitude. We bootstrapped it a while ago, maybe the first lecture. Okay, and I define these CST over ST plus CTU over TU plus CUS over US. Okay. And remember, CST, CTU, CUS, we're just linear combinations of CS, CT, CU. Okay, so like these C's are just color structures, like different ones, but combinations of the basic ones. Okay, so you can already see like it's easy. You just rearrange this thing into this form. Okay, I'm not even going to bother doing it, but here's one way you could do it. Okay, so you could take CS. You could use the fact that CST minus CUS, so let me not draw an error here. CST minus CUS equals CS. Okay, so I'm just going to tell you in words what you do. CS is equal to this combination. So take this formula for CS, plug it into that CS. So now it's in terms of these objects. Do the same for CT-CU. Okay, so now you have this expression in terms of CST, CTU, CUS, and you can just solve for the numerators for NS in terms of all these kinematics. Just look left-hand side, right-hand side, just check. Okay. Let me not do that here because it's just a bunch of algebra. Now in the end, what do you get? Okay. So maybe not quite the end, but let me imagine like looking at the CST part of left-hand side and right-hand side, looking at the CTU part of left-hand side and right-hand side, and the CUS part of left-hand side and right-hand side, and you get a bunch of equations. And those equations look like this. TNS minus SNT equals angle 1, 2 squared, 3, 4 squared. Okay, you should think of this came from left-hand side, like the calculation, because we computed the amplitude. This side came from the structure of this ansatz. Okay, so those would be setting those equal to each other. And then we have kind of every, looks almost like the cross product rule. It is cross product rule. Same thing. And this is S and U minus U and S. Same thing. Okay, set of equations. Okay, now I can take this set of equations and write it maybe in a slightly more compact way, a little slightly more illuminating way, as a matrix equation, NS, NT, and U. Right, it's linear in NS, NT, and U, but it's multiplying some matrix, which is T minus S, 0, 0, U minus T, minus U, 0, S. And this is equal to 1, 2 squared, 3, 4 squared, times 1, 1, 1. Okay, 1, 1, 1 being this is the same function 3 times. Okay, I just rewrote this in terms of a matrix equation. Okay, now, of course, what was the point of this? The point is we were trying to solve for n's, right? NS, NT, and U. Okay, and we're almost there. I just have to invert this matrix. But this matrix isn't invertible. This has vanishing determinant. Its determinant is S plus T plus U equals 0. That may seem troubling, but you knew this had to happen. Why? We know that if we shifted NS, NT, and NU by S, T, and U, it doesn't affect the answer. Okay, so that's exactly that flat direction. That's the freedom of these field redefinitions, or sometimes called generalized gauge transformations. Okay, so this is not invertible, but that's okay. You can still find, in some sense, it's underspecified. You can still find some NS, NT, and U that satisfy this equation. Okay, you can hit this, for instance, with a pseudo-inverse, and you have some freedom, okay, remaining in your NS, NT, and U. In other words, NS, NT, and NU are not uniquely fixed. That's okay. Now let's say you solve for them, and you make a choice. Okay, I'm going to make just a completely arbitrary choice, but the point is it doesn't matter what choice you make. That's what we proved on that right board. Here's the choice I'll make. Just, if you like, you could solve these sequentially and get these. So that's another way of just doing this more simply. I want to have NS equals, so you just solve this squared, be 4 squared over U plus NU S over U. NT is plus this 1, 2 squared, 3, 4 squared over U plus NUT over U. Okay, so NS and NT are solved for in terms of NU, which is arbitrary. Okay, I told you there was some residual freedom. That freedom I've chosen to put into the third numerator and literally make it any function you want. It doesn't matter. Okay, it corresponds to the freedom of changing gauges. Okay. Now, you can just check explicitly. If you take NS plus NT plus NU, NS plus NT plus NU, okay, these exactly cancel. This is NS plus NT. Sorry, this gives me NU S over U plus NU T over U plus NU, which is precisely proportional S plus T plus U, which is 0. Okay, we did the calculation, we checked. Okay, now what's the point of this whole story? The point of this story is for 4-particle scattering, which is what we've just considered, automatically the numerators satisfy a kinematic Jacobi identity. Okay, these are momenta. These are not colors. These are momenta. Okay, but it satisfies this, it equals 0. Okay, now here is the big leap, and I think you can anticipate what I'm going to do. Well, we have objects CS, CT, CU. Okay, right, just put it in parallel. We also have CS plus CT plus CU. CT plus CU equals 0. Okay, we have N and C. They're dual. Okay, dual in some kind of broad sense that they satisfy the same algebraic identities. The structure constants are similarly antisymmetric, and they satisfy Jacobi. So let's just do what we did at 3-point. Let's blindly replace one with the other. Let's just see what happens. Okay, so if you do that for, let's really parallel with what we did last time, for the 3-particle. Let's first take the kinematics, that is to say the NS's, and NT's and NU's, and replace it with more color. Okay, so let's say you took A4, and I said, okay, let me just double up, take NS, and replace it with another factor of C over S, plus C, T squared over T, plus CU squared over U. Okay, these are numbers, like literally numbers, like tensor of numbers, tensor of numbers, tensor of numbers. This, of course, is the 4-point amplitude in bihedron scalar theory. Okay, this is just the S channel, T channel, U channel exchange for a phi cube theory, and the coefficients are just the product of the structure constants. Okay, that same theory I wrote here, which is now erased. Okay, good. That's simple, maybe not too surprising. There's a much more surprising fact, which is the one I'll try to unpack much more in this for the remainder of my lectures, is, you can already anticipate, is if we take the colors and replace them with kinematics. So ns squared over s plus nt squared over t plus nu squared over u. Okay. So I have a new theory. It has no color. It's colorless, but it has squared numerators. So whatever number of derivatives you had before, number of momenta, it has increased. Okay? If you check the number it's increased, it has exactly the power of gravity, and this is exactly the graviton scattering amplitude in Einstein-Hilbert theory, in just general relativity. Okay? Now I hope that this is surprising to you, that this would work. Okay? You're not allowed to just take random parts of topologies and square them and get gauge invariant things, right? If you took QED, took one topology, like all the topologies, just squared them, things get messed up because the whole point of word identities is that there's like interplay between terms, okay? And yet, I'm kind of locally going to each term and replacing things and still getting a completely gauge invariant answer. That's incredibly surprising. And isn't explained by the fact that GR and Yang-Mills are rigid. I mean, they're both rigid, but why do two rigid things have to be related by such a simple mathematical set of operations like plus and times? Yes?
You might mention that you go back to the so-called K accumulations which you derived.
Very good.
in string theory, right?
Yes, yes. So I was going to cycle back to that, but there's kind of two flavors of this kind of double copy. The original, I mentioned BCJ, but I didn't talk about KLT. KLT, in really also wonderfully, beautifully seminal papers, studied open and closed strings and used open string, closed string duality to show relations between string amplitudes. In their field theory limit, they exactly become, well, actually not these identities, but a separate type of squaring relation, which is not at the level of these topologies, doesn't have a kinematic algebra or a Jacobi identity component, but is just taking products and sums of amplitudes. Okay. I don't think I'll be able to cover it, but it's in some sense very closely connected to this, but it has kind of less, at least to me, offers less insight into there being some underlying kinematic algebra, but massively powerful. The thing about KLT is it hasn't quite been understood how to generalize it outside of beyond tree level low loop order. This thing, as I'll tell you, can be recycled into loops and so on and so forth. So they're definitely intimately linked. And I should also mention, I mean, this is for those who know what KLT is. The KLT relations also double copy pions. So this is maybe not super well known, but if you just take those relations and apply them to pions, you will get these other theories. So that's also kind of cool. So this kind of massive universality of squaring applies also to KLT. Yeah. Okay, good. Any other questions? Yeah.
So switch it a little bit. I mean, so you're showing that the C's and the N's can be swapped
Yeah.
back and forth. But the C's came from these structure constants for whatever gauge group, and then the N's we said came from non-equivalent polarizations.
Right.
Couldn't you just think of the N's as also coming from structure constants of
Yes. Absolutely. So indeed, like that is the enticing theory question. Okay. There's a Lie algebra for color. There's a structure. Okay. The beautiful mathematical structure. The color algebra. What is the algebra for kinematics? So this is literally called the kinematic algebra. This is the puzzle. What is the kinematic algebra? What is its commutator? What's its killing? What's the bilinear form? Like all these like basic questions you'd ask. What's the Casimir? Okay. We don't know those answers in general. Certainly, I would say not for gravity, but I will talk about it for the case of pions and give you a much better explicit field theoretic explanation for what that algebra is. Okay. And others have thought about related ideas too, I should say. We're all thinking about this kind of collectively. But indeed, that's the question. What is going on? Like why is this happening? Not just like, is it happening? Okay. Now, I should say, this is not an accident of 4-point. This is a fact about any n particle. Okay, yeah, I have it here. This is true for any n point. Okay, and let me say quickly, just because it's hard to go through the example, but I'll hopefully give you enough to understand it. Okay, so yeah, if this was just 4-point, I wouldn't care. This is proven for any n particle scattering. Okay, so in other words, I can get you the 20 graviton scattering amplitude through algebraic manipulations of plus and minus. If you give me the 20-point Yang-Mills amplitude, which we've already computed through other ways for colliders. Okay, so that's what I was saying. It's a cheat code. We already have this whole basis of understanding of gauge theories. We can just lift on that. But first, let me just quickly tell you how this works at endpoint. Okay, endpoint. So at endpoint, this is what you do. Okay, let me start with biadjoint scalar, because it's like the you can see it's the scaffolding upon which other things are built. You could think of it as I started with a biadjoint scalar, took a color, replaced it with one kinematic. That gave me Yang-Mills. Then I replaced the other one, and it gave me gravity. Okay, so this is like tree, like how much do I want to replace at a time? If I took an endpoint, what you do is, it's kind of what you'd expect, but let me just say it. You write it as all cubic topologies. Okay, so like, okay, so all, what is it, 2n minus 5 double factorial cubic topologies. Like it's the analog of ST and U, but all the cubic topologies at 5-point. And like explicitly, there'd be things like this: 1, 2, 3, 4, 5, and permuting 1, 2, 3, 4, 5 in various ways. Lots of terms. Okay. Okay. But for each term, there's a numerator. Okay. There's a coupling constant, which is ci squared, which is just given by the color structures, and then di is the propagators. Okay. So like should be obvious. Like it's easy to compute in this theory. It's phi cubed. You know exactly what the C's are. Every topology is associated with a color structure and some set of propagators. Okay, very easy. Okay, but this is the scaffolding upon which you want to build the more interesting theories. Okay, is it clear what I meant by this topology? Okay. Now maybe I'll say this. This should hopefully be obvious. But you could have topologies, and you could look at their color structures. So take the color structure of this guy and subtract the color structure of this one. Okay, this means like swap like 1 and 2. So this is like 2, 1. This is a Jacobi identity. This gives me the color structure for this. Okay, hopefully these diagrams, you understand what these are. Each vertex is an FABC, and I'm just using Jacobi identity. Okay, this is the 3-term Jacobi identity. And this is me relating the color structures associated with each topology, and they satisfy it because I have color. Okay. So hopefully that's just all self-evident. The point is, we're just going to copy and paste this story onto Yang-Mills. Okay, what does that mean? That means we write the Yang-Mills amplitude exactly the same way. Okay, so we write A Yang-Mills n. We write this as Ci Ni over Di. Okay, where Ci is going to be one color structure because Yang-Mills doesn't have 2 colors but 1. These are numerators that depend on kinematics, and these are the propagators. So the Ci and Di are exactly the same Ci's and Di's here, okay, because that color structure is very similar. It's the copy essentially. But Ni are the kinematic pieces. Okay, so here's what I'm saying. Like super explicitly, compute the 5-point Yang-Mills amplitude with Feynman diagrams, if you so care to choose. Do that, write in terms of topologies, cubic topologies, and you'll get some numerators. Okay. Now, something funny happens at 5-point that's different from 4-point. At 4-point, we automatically had this Jacobi identity. Like whatever, no matter what we did, we got this equals to 0. Something really interesting happens at 5-point, which is that if you just pick a random gauge and look at Ni plus Nj plus Nk. In fact, let me call this like Ci, Cj, Ck. I'm gonna scramble some signs, so don't worry about that. You will find that it's generically not 0. If you pick a random gauge, it's not 0. Okay? But if you rearrange your terms inside the sum in some special clever way, or there's actually a whole family, infinite family of ways, there's an algorithm to do this. But if you arrange it in a way such that this is 0, okay, so this is now a constraint. I'm like choosing numerators, and I'm sprinkling my quartic vertices around precisely to accommodate this at endpoint. Okay? Then if you like, I found some field basis, so to speak, where the kinematics and color are in parallel and satisfy the same identities. And you have to do this for every single identity. Okay, so for every, you can see here that I So like this is like a 4-point subdiagram. I haven't even touched. Sorry, sorry. I haven't even touched this last guy. So I'm basically looking at a sub 4-point diagram and checking the Jacobi identity. Here you have to check for every subdiagram, like inside, and make sure that this is true. Okay? Again, this is it. There's no way we do it on the board in real time, but this is what we do. Once you find those numerators, okay, which is not hard because you just have to find a choice, shift your numerators to make this 0. In other words, you have to introduce an alpha, it's gone now, such that this equation is vanishing. So if you like, it's still a constraint, a linear constraint you can impose. Once you have that, then you can double copy it. Okay, and the statement is that at endpoint gr is equal to this times ni over di. Okay? So basic story is take your kinematics, put them into a form such that they exactly have dual algebraic identities that are satisfied by color, and then just replace as you like in any theory. And you get a consistent theory at endpoint. So this is proven with BCFW, recursion, with factorization, CHY. Okay, this has been proven like 17 different times for tree-level scattering amplitudes in gauge theory and gravity. I'll get to loops shortly. Okay. Oh, we're just about at the end. How much time? Like literally 0?
15 seconds.
Oh, 15 seconds. I needed like 16 seconds, and then I just said this. So let me just continue. We'll continue the story. We're going to keep going. But the upshot will be that this whole mechanical procedure, we're going to do this next, also holds for pions, photons, Yang-Mills, Einstein, basically every theory you know, the same trick works. The plan for the next set of lectures is the following. I'm going to show you how this works mechanically for pions, because it's a case that I'm especially interested in. I'm then going to tell you about interesting other connections, which relate to the fact that gravity, gravitons, pions, gluons, these are all connected in another way, linked through amplitudes. In some sense, the mantra here is that if someone handed you the graviton amplitude, you could get all the other amplitudes from it directly through some trivial operations. So they're linked, even pion amplitudes, all these amplitudes I'm talking about. And then at the very end, I guess this is going to be my last lecture, I will give you a quantum field theory explanation for some of these double copies at the Lagrangian equations of motion field level. Okay, I'm going to try to give you some satisfaction. And that is to say, for some theories, and particularly the nonlinear sigma model, I will tell you what the kinematic algebra is, why it works, and how to double copy at the level of fields for that theory. But there's still many open questions, which I'll tell you about in that next lecture. So I'll stop there. Sorry for going slightly over. Thank you.
I had a question about over on that board that's now erased, you have like a thing where you have like delta n over s.
Yeah.
Must be concept. It feels like a scale invariance kind of a thing. Is that
Yeah.
imagining that?
Yeah, that might be what do we call that, hallucination in machine learning? It looks like it. I had the same feeling. It looks like some kind of projectiveness of it up to some arbitrary coefficient. Just so I understand, the question was, is there any notion in which I should think of this as like a rescaling or something? Yeah. Let me say, I don't think so, okay? But I should think more deeply to give you I'm sure it's hard to know when structure means something. To me, it's more the pedestrian, this is the only thing that can add to 0. But let me think about it. I suspect there isn't some deeper meaning behind it, but although I do see the kind of pattern in equations. But kind of what you're doing is exactly what we do all the time in amplitudes, which is great. It's like you see a thing and you make a connection, and since you're unmoored from you're far from shore. You have no Lagrangian to help you. You're flailing and you're what does that mean? And sometimes picking at that actually tells you cool things. So let me not dismiss it. Let me think about it. But certainly not in my mind do I know if that's a connection that can be made. Yeah.
All right, well, let's thank Cliff again. We can enjoy our coffee break, and I'll see you back in a half an hour.
Yeah.
Well, related to the earlier question I had, which is what are the structure constants of kinematics? Like, if I were to squint and I were to ignore that there exists a real world in which objects with momentum
Right.
mean anything,
Right.
if instead I go fully into like the Wigler classification